Good afternoon, folks. I hope you've been enjoying the conference so far. I'm going to talk to you about the continuing future of C++ concurrency. I'm going to start with what's new in C++ 14 since the C++ 11 standard. Obviously, the first standard that acknowledged the existence of concurrency was C++ 11. So C++ 14, the first time we actually added new stuff to that. And we've got new stuff coming in C++ 17 as well. And then, of course, a bunch of technical specifications on concurrency, parallelism, and transactional memory. So I'm going to give a brief description of some of the contents of those as well. Yeah, there is a continuing future for concurrency in C++. And so that's what we're going to talk about. In C++ 14, we actually only added one new concurrency feature, and that was a shared timed mutex, and then the corresponding RAI lock type, shared lock. So those of you coming from a POSIX background might know about the Pthread read-writer mutexes, or on Windows, the slim reader-writer locks. And that's essentially what this wraps. Multiple threads can hold a shared lock, or alternatively, one thread may hold an exclusive lock. So if you've got it's typically an optimization for a data structure that's read most often and then updated rarely. So you can have multiple threads that are reading concurrently, and it's all safe. But then when you want to update everything, then you say, hang on a minute, all of you reading, none of you can read whilst I just change this. And then you can all go again. It's got timed in the title because some of the functions have timeouts, so you can say, try and acquire a lock for a certain period of time. In C++ 7, we've got standard timed mutex and standard recursive timed mutex. So this is not a new thing, the concept of it being a timed mutex. So yeah, those functions with the timeouts are there for both the exclusive lock functions and then for the shared lock functions. So you can try and acquire a shared lock for a certain period of time. You use it like this as an example. So we've got some data structure that we're trying to deal with. We've got in this case a table which a map of strings to strings. We have our shared time mutex at the top, and we're implementing some function to find an entry. So this is a read operation. We're finding. So we're going to take a shared lock, and we're going to use that nice new RAI type shared lock on our shared time mutex. Construct our guard. We're going to find the entry in the table. We're going to throw if we didn't find what we were after, and if we did find it, then we're going to return the second value. I mean, that's just a standard map lookup. But the whole point, the bit that's specific to this is we've got this shared lock on the shared time mutex. On the flip side, then if you're adding an entry to this table, then again we're going to want to protect it. This time we want an exclusive lock. So we've got our lock guard, the same lock guard that we would use with a standard mutex. It works with a shared time mutex because it implements the lockable concept. So it just works. You just stick it in there, and this then acquires the exclusive lock. Once the exclusive lock is acquired, none of the readers will. It will wait until any current readers have released their shared locks before you proceed, and then no new readers can acquire shared locks whilst the exclusive lock is held. So our adding of an entry to the table is perfectly safe. We don't have to worry about the concurrent readers on that table. Like I said, there's a timed part. So the shared lock RAI type allows you to put that as part of the constructor, just like unique lock does. So you can say, I'm going to try and acquire my shared lock, in this case for 1 second, if you don't get it in 1 second, then the shared lock just doesn't own the lock. And so then if you use this try lock constructor, you then have to query it. Did I get the lock? Does my shared lock own, no, SL.owns lock? And if I didn't, then I can't do whatever it was I was trying to do. And so you have to give up and do something else. And again, typically you'd want to use this where you've got some sort of, well, I've got a certain amount of time in which I can do this bit of processing before I need to do something else, whether it's update the screen, respond to an event, or do something. But if I can't get my lock within that period of time, typically it's not going to be seconds, it's going to be milliseconds. But anyway, so if you can't get the lock within a certain period of time, then I'm going to give up and I'm going to do something else. And typically that's where I need to do this eventually, but if I can't do it right now, then that's okay. That's not a big problem. I'll do it next time, because I'm going to call this function in a loop, and every time I'm going to try and acquire the lock, and if I succeed, then I can do it, and if I don't, then never mind. And that's just the general principle. That's why we have these time functions in the standard for the standard mutex anyway. Obviously for timed mutex rather than just plain standard mutex. So it's the same applies with shared timed mutex. So it's not a new concept there. There is a question already, yes. So the question is, are we going to use shared lock for reading purposes and lock guard for writing purposes? And yes, that's in general true, because for writing purposes, you want an exclusive lock, and so lock guard and unique lock are the types that give us that. And for reading purposes, you want the shared lock, and so the standard shared lock guard is what gives us that. Would the better name have been read lock and write lock? Who knows? That's water under the bridge. This is what we've got. So on this side, we say profile, profile, profile. It's all about timings. Now, fundamentally, the reason why you would want to use a shared mutex is because you're trying to optimize for the case where you've got lots of readers and an occasional update. And you're trying to do this isn't trying to be an optimization. But in order to keep track of all your readers, every time you acquire a read lock, you've actually got to update the mutex itself in some fashion to say, I've got another reader. And then when I'm done, you've got to say, that reader's done now, so any exclusive lock people who are waiting can now take the lock. So there's actually still the contention on the lock itself. So you need to profile to make sure that you are getting the optimization and the performance benefit you hoped you would. Like any optimization, profile beforehand, profile afterwards, you might find in your case that it's actually better just to use a plain standard mutex. And this will probably vary between platforms, and possibly even with standard library implementations on the same platform. So you need to, if you're porting across multiple platforms, you need to profile on all the platforms as well. So C++ 14, that was all there was to it. Concurrency in C++ 17, we've got a little bit more. So we've got shared mutexes, shared timed mutexes, non-timed, standard shared mutex. We've got a new variadic version of standard lock guard, and then a nifty C++ 17 feature, which it's not a concurrency feature, but it works nicely. And that is that you can deduce your template arguments for class templates from their initializer. So standard lock guard doesn't require you to specify the mutex type anymore. And neither does standard unique lock, or standard shared lock for that matter. On top of that, we've got parallelism. The Parallelism TS version 1 has been merged into the C++ 17 working draft. So there are now parallel versions of most of the STL algorithms. And also say, for anyone who's been following the standardization process, and was hoping for joining thread, you're not going to get it unless somebody resubmits the proposal and the committee changed their mind. No, it got voted down at the last meeting. So sorry, we're not going to, doesn't look like we're going to have standard joining thread after all. So we got shared time mutex. Why do we need shared mutex? And the answer is, of course, performance. On some platforms, notably Windows, I think, then if you don't have to support the try lock with timeout, then you can actually make the implementation cheaper overall. And so you can get better performance if you're never doing timed operations. And given that that's probably most of the uses, never use the timed operations, then that's a potential. And yeah, and you're using this for performance in the first place, so having your, making sure that it is as fast as it can be for your use case is probably quite important. And the reason that we didn't get it in the first place is just a matter of history and how the committee works. So as far as variodic lock guard goes, this is great. If you're trying to do an operation that is going to be, needs to acquire multiple mutexes, then if you specifically lock them one at a time, then that's a classic deadlock case. You try and lock mutex A, and then you lock mutex B, and in one thread, and somehow another thread locks B and then A, and everything goes wrong, your program grinds to a halt. So in C++11, we had this standard lock function. So you could give it a couple of 2 mutexes, 3 mutexes, 5 mutexes, and it would work out a way of locking them all in a deadlock-free fashion. But in order to use that with your RAI guards, like standard lock guard and standard unique lock, then you then had to either do the lock first and then adopt everything afterwards. You split over multiple lines, and it's easy to get wrong and make a mistake. So with the new variodic lock guard, you can do that all in one line. Standard lock guard, mutex type 1, mutex type 2, and then your parameters. And this uses the same underlying acquire all the locks without a deadlock mechanism that standard lock does. But it's all already owned by the lock guard, so you don't then need to worry about making sure that things release when you get to the end of the function. And like I said, C++17 also gives us this implicit deduction. So you can specify still standard lock guard of standard mutex. And it just works, but that's fine. But you can also omit that now. The class template type deduction means you can just say standard lock guard, no template parameters. And that is great. If you're, it simplifies typing. It means if you change the type of the mutex from standard mutex to standard timed mutex because somewhere in your code you realize that you need a timeout, then that's now just going to work. And all the uses of lock guards, you don't need to go through and update them all. So yeah, and that obviously applies. I mean, it's a general feature from C++17, so it applies to all class templates that can be deduced from the initializer. So it applies to standard unique lock and standard shared lock as well. Okay, so that's C++17 out of the way. So let's move on to some of these TSs. Concurrency TS version 1. Now this has actually been released as version 1. It is a published ISO TS. That gives us a few things. Gives us continuations on our futures. So you can say, here's my future, and when it is ready, then I want to do some other asynchronous task. you can say, I've got a bunch of futures, and when they're all ready, then I want to do something. I'm going to wait for all of them to be ready, or for the first one out of a bunch to be ready. So there's functions to give you that, the sort of set joining facility for gathering futures together, which is incredibly powerful too. And actually, combined with the continuations, that is a great combination, because you can say, when everything's ready, then schedule this new asynchronous task. And that task will only start when all the features are ready. And then we've got latches and barriers for providing scheduling points within our code. So when a whole bunch of threads have reached a given point within the code, then we can move on. And the latches and barriers give us those synchronization points. And then finally, we've got atomic smart pointers in the form of atomic shared pointer and atomic weak pointer. So whereas in the C++11, a single shared pointer instance, you cannot have two threads accessing map, because otherwise it's a data race, unless you obviously wrap it with a mutex or some other synchronization. If you use the Concurrency TS, then you can have atomic shared pointer, so that you can then have multiple threads access that without external synchronization. But there's also a whole bunch of things coming up for Concurrency TS version 2. Now, these are all proposals under consideration. The working draft for Concurrency TS version 2 is somewhat scant at the moment. We've got the big thing, really, from my perspective, is the executors and schedulers. Now, this is the fundamental building blocks which are going to get us thread pools. Thread pools and things like that are things that we have been wanting as a concurrency group for concurrency support in standard TS since we were working on C++11, but we ran out of time to specify them properly, and so all we got was standard async. And as a group, people have been working on them ever since. There have been many, many proposals and changes to the way the API works around executors and schedulers, but we're really, really keen to get them, and so hope we're going to get them sometime soon, actually, in an API that we can all agree on. There's also proposals for distributed counters. So obviously, if you've got hundreds of threads and they're all trying to update a single count, then that's an epic point of contention, and that's going to cause everything to slow down. So you don't want to do that. So if you don't need everything to really, really, really be up to date, and you can cope with batching things, then you can have your distributed counter, and you say, well, here's this counter that we're eventually going to update, and this thread is going to, it updates its local count, and then the propagation to the central count then happens automatically in some fashion. And obviously there's ways that you can say, update it now, please, because I really care. But it means that it provides you the eventual consistency on the count without the direct contention that you might otherwise get. Also, we've got proposals for concurrent unordered containers. So in the standard at the moment, we've got unordered map and unordered set. And there are proposals to provide concurrent versions of those so that you can do your table lookups. So the example that I had with the shared mutex, then it used a standard map, so it's not quite, but if you use the unordered version and the proposed concurrent unordered version, you wouldn't need to put mutex lock in, because that would deal with internally in the container. It is potentially possible for some implementations for that to be lock-free. So it depends quite on the API and whether the implementations then provide those, but there is potential for that. Similarly, we've got concurrent queues. Now, obviously, so concurrent unordered containers and concurrent queues give us basic building structures for lots of cross-thread communication. So again, it's all about you not needing to use a mutex yourself because the containers and data structures take care of it for you. And queues are great you can use them for message queues, so you can have communicating state machines, whores communicating sequential processes, so you can have each thread essentially communicates only with the outside world through a queue of some description. So once you've got that, then you don't then need to worry about lots of synchronization problems. And then we've got safe concurrent stream access is coming, we hope, and there's certainly proposals for it, so that you can say, here's this bunch of, I'm running on a thread, I'm writing stuff out to a stream, I know that another thread is also going to be writing stuff out to a stream. Here is a bunch of stuff that I want to make sure it appears together, but I can't do it as a single insert, and so we're providing some mechanism for ensuring that a write is then atomic from the point of view of the outside world. Resumable functions and coroutines. There's a whole bunch of talks on that today. The guys I spoke to yesterday had put up a slide and said that it was like a mini coroutine con. So yeah, there's a whole bunch of stuff on that. That allows you to simplify code, again, with asynchronous stuff. If Hartmut had a slide up yesterday about the making asynchronous parallel algorithms and how sticking co-await when you got two parallel algorithms that you got with futures that you're waiting on, so that you could then, and that would allow the outer function then to also return a future without you then having to worry about making sure they were both ready. In that particular case, he could have used when all and continuations as well. But coroutines are an alternative. In some sense, they provide you concurrency on a single thread because you can switch between your different functions. When you haven't got work to do on this function, you're waiting for something, then you can run something else. And then pipelines. So we've got a sequence of data coming in, and we've got a sequence of operations we need to do to it. So we build a pipeline, and we say, do this, and then do that, and then pass a result to this other thing, and then split it out and pass the result to these two other functions that run in parallel, and then combine the results. And those of you that do command line processing in Unix pipes, but actually in your code, in your C++ program. So obviously, it's great if you've got a whole bunch of data coming in and you do the same sequence of operations on every bit of data that comes through. Okay, so I'm going to have some actual more concrete examples of some of these things. Everything in the TSs is in the standard experimental namespace. That doesn't mean that it's poor code and that you shouldn't use it. It means that it's an experimental interface. The C++ Standards Committee aren't committing that this is what it's going to be like when it gets into the final standard. So don't let that put you off. I know that some workplaces have an experimental namespace for their own bits of code where don't use this in production, they say. Well, just because it's in standard experimental from the point of view of the standard doesn't mean that. Obviously, you hope that if whichever implementer you got your implementation from, you hope that it's as good quality as the rest of the stuff they provide you. In the slides, I'm going to use stdexp instead because standard experimental is a bit long for on-slide examples. Okay, so continuations. Continuations give us a new task to run when a future becomes ready. And conceptually, you say, when the future is ready, then do this. And so, sure enough, the function is called then. If you start with a standard future, well, if you start with a standard experimental future, because they only work on that, then your function then must take a standard experimental future as the only parameter. And the source futures are one-shot things, so normally if you get the value from a future, then that future is no longer valid. So similarly, if you chain a continuation on a future, your source future is no longer valid because it is going to be passed into the continuation. And instead, you've got a new future to hold the result from the continuation. And all this means that on any given future, only one continuation can be added, but of course, you can chain them. So here's some code. We're going to try and find the answer. We all know it's going to be 42, but we're going to assume that we haven't got there yet. And when we do get the answer, we're going to process the result. So we use standard experimental async to find the answer, and that gives us back a standard experimental future. We can then say, then process the result, and that gives us a new future, f2, which processing the result is returning a string. So f2 will be a standard experimental future for a string. And at this point, f is no longer valid because it's been swallowed into the continuation. When the original async task returns, then it will pass the resulting future holding the result as that parameter to process result. So we can see it takes standard experimental future of an int as its one and only parameter. So that's where that is conceptually where our future f goes. It becomes the parameter to that function. Yes. Okay. So the question is, can you add parallel thens to a single future? So you can say f.then to get process result, and then also f.then something else. And the answer is no, you can't, because after your first f.then, your f has no future in it. It's invalid, so you can't then do that. You can chain onto the result of f2, but you can't have multiple parallel thens on a standard experimental future. If you want to do that, you can with shared futures. But we'll look at that in just a second. Continuations also allow you to process exceptions. So if your first function throws, then that gets stored in the future like it normally would, and this is stored in the future that is passed to the continuation. So we have standard experimental async of fail. Fail is going to throw a runtime error. We then chain on the continuation next. Next takes the future. That will be a future that is holding the exception of the standard runtime error that was thrown. And so when you call f.get inside next, then that's going to throw, because f.get throws if the future holds an exception. And then obviously in foo, then the final future is the one returned, holds the result from next through, and so you actually end up, the exception propagates all the way out. So the final get in foo will also throw an exception. Obviously, if you catch the exception in your continuation, then you can do whatever processing you like with it, which is why we pass in the future rather than passing in the value, so that this exception gets propagated too, and you can then process it or allow it to propagate out and pass on to the next continuation in the chain. If you've got some function that doesn't take a future, so your process result wants a raw int, well, you can just wrap it in a lambda. So your lambda takes a future. If you use the new generic lambda, so that could say square brackets auto f, so to take the future, and then obviously you can process the result, unpack, call f.get. It's a little bit of overhead, but it's not too tricky. Okay, so continuations work with shared futures as well. Someone said, can you have multiple parallel thens on the same future? Well, with shared future, you can. Obviously, if you started with a shared future, then the continuation must also take a shared future. And shared futures are reusable, so and calling get on a shared future, it's still usable. Same applies, you add a continuation, it remains valid, so you can have multiple. So same example here, we've got async find the answer. We're going to call .share so that fi is a standard experimental shared future of an int. And then we are chaining two continuations. These will run in parallel. So as soon as the original async has finished, then the tasks for next one and next two will both be scheduled. I'll say at this point that the scheduling is unspecified. The TS says that continuation tasks are run on an unspecified thread. The idea is that by the time we've got as far as integrating it into the C++ standard, then we will have sorted our problems with executors and thread pools, and so we will add to then a means of specifying where you're going to run your continuation. But for the meantime, it will run on some thread somewhere in your system. Yes, there is a question in the middle. What happens if one of them throws? Well, it's just a continuation, which is an async task wrapped in a future. So each continuation that if it throws, then the future associated with that continuation will capture the exception. So in this case, we've got two continuations, which are stored futures F2 and F3. Although actually on the slide I've called them F2 and F2, so that's just confusion. But each of those will, if next one throws an exception, then the next two task is still going to run, but the future associated with the next one continuation will hold the exception, ready to throw it when you call get. And obviously, if you then chain continuations on those, then the exceptions propagate down the one path where that exception went and not down the other one. Okay, so what if you wanted to wait for your futures? You can wait for any of them to be ready. You've got a whole bunch of futures and you want to wait for just one? Well, that's all right. That's what we've got to overload, when any. We've got two overloads. These are great big long signatures, but actually it's really quite straightforward. The top overload is a variadic. When any, and then you pass it any number of futures, and it returns you a result. Now, the result is a package that holds a tuple with all the futures that you gave it, and then a flag to say which one of those it was that was ready when it checked. Obviously, by the time you get around to processing it, they might all be ready, or 3 out of 4, or whatever. But there will be one that triggered the when any result, the future that's returned from when any to be ready. And the when any result has a flag to say, it was this one, the third one in the list. And by the way, here is the list. So it gives you the list back so that you can not only get to the one that triggered it, but also you can get all the others, and you can then process them, wait for them in turn if they're not ready yet, or do some other form of processing. The bottom overload also has a great big long return type, but actually it just when any on an iterator range. So you pass in a range, any iterator range, and it will iterate through and build your set. The result is always a vector that holds the futures that were passed in, regardless of where your iterators came from. Had a question at the front? Yes, so the question is, if a task associated with a future throws an exception, does it make it ready? And yes, with futures, if they capture an exception, they are then ready, and so then the when any will indeed trigger. And so if you've got 3 tasks and one of them throws, and that throws before the others have got the results, when any, and you pass those to when any, the when any result will be ready, and it will say, that one that threw is the one that's ready, the one that triggered. So this is great if you've got speculative tasks. If you want to say, well, I've got plenty of cores to spare, and I've got 2 possible ways of calculating this value, 3 possible ways maybe, and I don't know which one's going to be fastest today, so let's launch all of them. And whichever one gets back quickest, I'll take the result and then process it. So that's good. Alternatively, if you've got a whole bunch of stuff that you want to do, and when the first thing's ready, then I want to do some more processing, and then when the other bits become ready too, but I want to process I don't know which of my 3 things is going to be ready first, and so I want to process the one that comes back first, and I want to do that processing first. So I could chain a continuation on each one individually, but actually I want to only process one of the results at a time. So I'll say when the first one comes back, I do the processing and then wait for the second and third in turn. And it allows you to not fuss about which order. So we launch 2 things with async. F1 and F2 give us our tasks. And then these are standard futures, or experimental futures, and so we have to move them. We move them into our whenAny call, and then we get back a future that holds the potential, the whenAny result. We can, it's an experimental future, so it can, of course, chain it with continuations. So we can say f3.then, do some processing. Okay. When all is the counterpart. You wait for all your futures to be ready. And again, it's got 2 overloads. First one just takes a bunch of futures as parameters, and the second one takes an iterator range. And again, the result holds a vector. This time, because the results are all definitely all going to be ready, you don't have to, there's not this whenAny result complicatedness. The first one is just a future holding a tuple, and the second one is a future holding a vector of futures. And this time, it's great if you've got a bunch of subtasks, you want to launch them off, and then when they're all ready, then you've got some more processing to do. So you do exactly that. No, here's our 3 tasks, subtask 1, 2, 3 with async, and then when all, get the result. Or chain a continuation, or whatever. Okay, it's not the only changes to the futures interface. There's a collection of little changes we've got. First up are 2 functions to create futures that are already ready. Make ready future that gives us a future that holds a value. So rather than actually spawning a task, you say, well, I already know what the result's going to be, so here we are. And then the counterpart for that, which is make exceptional future, which is, I'm going to create a future that's holding an exception ready to throw. So if anyone dares call get on it, then it'll throw up in their face. And again, these cases where, as a general thing, you've got an API and a library structure that uses futures for communication, and in this particular code branch, you realize you know the answers already, you don't need to actually spawn any tasks to do it. So rather than having to do a little dance of creating a promise and getting a future and setting the value on the promise, or setting the exception on the promise, then you can just call these functions instead. And then we've also got this nice little nifty function, is ready. We can ask a future, are you ready? We can pull it rather than having to wait for it to be ready, or do a nifty little dance with saying, wait for no seconds to see whether you're ready. Then we can just query, are you ready? Okay, next on the list is latches and barriers. A latch is a single-use countdown. You say, well, I've got this bunch of events that I need to happen. And then when all the events have happened, I can do some more processing. And so it counts down. And as each thread does the things, it says, count down the latch. And then you can have another thread or some number of threads waiting on this latch. And then as soon as the counter hits 0, all the waiters are notified and everyone can proceed. It latches, it's permanently latched, so it's a one-shot thing. Whereas barriers, on the other hand, are a reusable mechanism. And this time it's where you've got a bunch of threads that are waiting for each other in some sense. So if you've got a multi-stage process and all the threads need to have completed stage A before they can all move and do stage P, then you create a barrier, and at the end of, so you say here's barrier for 5 threads. Here are my 5 threads. Each of them will arrive at the barrier. When all of them arrive, then they all can proceed. And then if this is a cyclical process because of the way you're processing your data, so then they've all proceed and they do the next. So you've got a packet of data coming in. So 5 threads all do their parts on packet A. When they've all processed packet A, they all arrive at the barrier, and then they could all then move on to process packet B. And then again, when they've all done through packet B, then they all arrive at the barrier, and then again, they're all released to move on. Final thing in the concurrency TS is atomic smart pointers. Now, shared pointer and weak pointer are not bitwise copyable because they've got to deal with the reference counts. So you're not allowed to say standard atomic of standard shared pointer or standard atomic of standard weak pointer. But it would be really nice if you could. And so in the TS, we've got standard experimental atomic underscore shared pointer and atomic underscore weak underscore pointer. And these are special types that provide the same interface as the standard atomic interface, but they actually work on shared pointers, whereas the standard atomic interface can't because it has to deal with the reference counting. And this you would use where you've got a single shared pointer object which you want to have multiple threads. Obviously, each thread can quite happily have shared pointer objects of their own, and they can even refer to the same thing, and the reference count will be dealt with accordingly. But if you've got a single object, like in a linked list, if the next pointer's in a linked list that's being traversed by multiple threads, then if you try and update those concurrently from multiple threads, then that's not going to work if you've got another thread traversing and you need to use external synchronization like a mutex. If you use atomic shared pointer, the synchronization is moved internally. And again, depending on what your implementation does, it may use a mutex or it may manage to be lock-free. Okay, so what's coming up? Proposals under consideration. So yeah, all these things that I've just done examples for are in Concurrency TS version 1. So that's actually an official ISO document. These things, some of them have been put in the working draft, most of them haven't, they're just proposals for discussion. So everything could change. Okay. Executors and schedulers. These are the building blocks for thread pools. An executor schedules tasks for execution, and you might have different properties. You might have thread pools, you might have serial executors that run things on a particular thread, one in after another. Hartmut talked yesterday about the potential for GPU executors. So you can say, here's a bunch of stuff, go run it on the GPU. Or Numera executors, so here's a bunch of stuff, go run it over on that particular node that has best access to this chunk of memory. So we're working on an interface that's going to work for all of these. I think there's a talk running at the moment that's talking more about that, so go and check if you're actually interested, go and watch the video afterwards. Okay, I said about distributed counters, we can attempt to improve performance by reducing contention on a global counter, by buffering the changes locally, and then only providing eventual consistency to make sure that the global count is eventually correct, but doesn't have to be correct right now. Unordered maps. I mean, proposal is concurrent unordered value map, which is a bit of a mouthful, but it does tell you essentially the essential properties. It's concurrent for concurrent accesses. It's unordered, so like the unordered containers, it uses a hash internally. it stores values rather, because all the standard containers that we have at the moment, then you can get iterators and you can get references to the contained values with the concurrent unordered value map. You can't get those references. All the functions that would return a reference instead return a value. And some of them return an optional value because the container might have changed. So the value that could have come back isn't there. And in order to simplify things, because they're not going to work with the standard algorithms, then they contain some algorithms themselves. So reduce and for each, for example, as member functions. The same way that standard list provides sort, because it doesn't work with standard sort. As I said, queues are a vital means of inter-thread communication, a building block for communicating sequential processes, as well as all sorts of other just general inter-thread communication. They may or may not be lock-free, they might be fixed size, they might be unbounded. There's a whole bunch of properties. The proposals give you lots of ways of tweaking that, so you can have lots of different queue types with all sorts of different properties. One nifty feature is the ability to close queues, because obviously, if you've got a bunch of work coming through and you can say, okay, I'm done now, done sending. So then the processing thread at the other end can say, yeah, okay, have I got more work to do? No, no more work. Yay, okay, I can finish now, and it helps you with cleaning up. The proposal allows that we have at the moment allows you to get a handle to just one end of a queue. So you can have a push handle where you can stick more stuff, and a pop handle for taking stuff that's ready. So rather than passing the queue round, then you can pass around these, and that's sort of a means of abstracting it, so it doesn't matter what the concrete type of the queue is, you can pass around a pop handle, and you don't have to worry about whether that was a pop handle to a bounded queue or an unbounded queue, or a lock-free queue or a lock-based queue. It doesn't matter from the point of the code that's doing the processing. And then they work with iterators as well. So there's quite a lot of flexibility in that proposal. Okay, save concurrent stream access. At the moment, if you use the standard output streams, then it is guaranteed that each individual insert is atomic from the point of view of the final output. But if you're doing multiple inserts, insert 10, 20, 30 as 3 separate inserts, and another thread does 40, 50, 60 as 3 separate inserts, then the 2 threads can now be interleaved. So you could get 10, 40, 50, 20, 60, 30. And obviously the 10 is before the 20 is before the 30, and the 40 is before the 50 is before the 60, but they're all interleaved across the 2 threads. So it would be nice if we could avoid that, and there's proposals around that. One of the proposals has basic O-stream buffer. The name of this type and the way it's specified keeps changing through the proposals, so what it's going to finally look like by the time it gets as far as a TS, I'm not sure. But the principle is that you create some buffer for what you're saying. I want to gather the output, I'm going to output it to standard cout, and now I can do a bunch of inserts, and the whole thing is then atomic from the point of view of the final output. It's to be used in conjunction with. He said, does it replace basic O-stream? And no, of course it doesn't. It's to be used. It will wrap another basic O-stream. So then, it's exclusively for this purpose rather than a general replacement. Coroutines. Coroutines are great. They expose a pull interface for callback style implementations. And reusable function, resumable functions is a way of generating async calls from code. So things like the co-await interface keyword. So you stick co-await in, and it says this function is going to resume when this other task is done. And there were alternative ways of structuring code that does asynchronous operations. Like I said, there's a whole bunch of talks on that. It has the potential for greatly simplifying things. If you do it wrong, it's also got the potential for greatly confusing people. So make sure you don't confuse your users. But yeah, there's a great potential there, and can simplify code quite a lot. The boilerplate, if you look at the boilerplate that's equivalent to lots of like using the co-await keyword, then you can say, I'm glad I didn't have to write all that myself, and the compiler's doing it for me. But you could, in most cases, and things are equivalent to standard async tasks and things. Okay, so pipelines, again, like Unix pipelines on the command line and things. So you have some inputs from a source. You have a sink where you're sending stuff, and then you create a pipeline which takes data from a source and then does a series of processing and dumps it out to the final sink. Again, these are all proposals, so the precise syntax and function names might change, but that's the general idea. Another thing that's coming up, and I really, really hope is actually going to make it into the next TS, is hazard pointers. And they fundamentally help us provide an answer to the question, when is it safe to delete this object? If you've got a data structure which is accessed from multiple threads, and you've got a map or a list or something, and you've got some node that you want to delete, some part of the data structure that you want to remove, then if you're running things in a lock-free fashion, then how do you know that somebody else isn't accessing it? So it's safe to delete. And hazard pointers help give us an answer to that question, because you declare, I've got a hazard pointer pointing to this object before you try and use it. And then if you want to delete it, you say, has anybody got any hazard pointers pointing to this object? And if the answer is yes, then you stick it on a deferred reclamation list. And if the answer is no, then you know you can delete it right now. It's an alternative to garbage collection and reference counting. So rather than using atomic shared pointer, you can use hazard pointers. At the point of use, it's potentially a little bit more complicated, but the potential for performance is much greater. So it's a trade-off, like most things in life. So yeah, this is how it works. You've got on the using thread, you obtain a pointer to an object. You mark that you're accessing that object X with a hazard pointer. You check that pointer you've still got is still valid before you actually dereference it. You then use the pointer in some fashion. You dereference it. You pass it to a function. You do whatever. Then when you're done, you release the hazard pointer, and if you actually, and then if X is marked for reclamation and you're on the reclamation processing list, then you delete that object if it's been marked so, and there are no other hazard pointers. If a thread is actually trying to do the deleting, deliberately trying to remove it from a data structure, then again, you start by obtaining the pointer, you mark that it is now to be deleted, and then you check the hazard pointers. And if somebody holds a hazard pointer, then you have to put it for reclamation later. Otherwise, you can delete it right now. Okay. There are plenty more proposals not covered here. If you want to have a look on the committee website, or go to the ISO CPP Foundation, because lots of the papers get published on, the links get published on there as they get released. And you can look through the archives to find the papers. So there's also a specification for parallelism. We've got TS1, which is now merged into C++17. Got parallel algorithms, including MapReduce, or something similar. It's called transform reduce. It's not quite the same spec as people might expect from MapReduce, but it does essentially the same thing. We have lightweight execution agents and the potential for SIMD and vector algorithms. For Parallelism TS version 2, the only thing that's concretely added to the working paper at the moment is task blocks, but there's more work being done. The C++ 17 library incorporates the version 1 TS, and that essentially provides us with a whole new overloads for for most of the standard library algorithms. They all have this execution policy as the first parameter. That execution policy can be one of three things at the moment. Sequential, which is just the same as a normal algorithm. Standard par, which is allows it to be parallel on multiple threads, and then parvec, which says, well, also make use of vectorization if you can. And I said the vast majority, it's a great big long list. I've highlighted in bold a couple of ones that are slightly relevant to people. For each is a good general one, but also merge for merging things, will find and copy and count, transform, reduce down at the bottom, sort. Most of the algorithms are there. Task blocks from Parallelism T2 are about managing hierarchies of tasks. So you can nest task blocks n deep, and nested task blocks can run in parallel. It's sort of fork-join parallelism. So, because all the nested task blocks within the task region are complete when it exits. So that's so you create all your nested task blocks, and then when you exit your block, then all those parallel tasks are joined. We have that fork-join parallelism, which is great for some things. So for recursive divide and conquer through a system, then that's great. There's also the transactional memory TS. Two basic types of transaction blocks: synchronized blocks and atomic blocks. And the synchronized blocks are sort of equivalent to as if there was a mutex around it, but it sort of makes it work so there isn't. Atomic blocks are lower level potentially, and then you have to deal with possible exceptions and whether they automatically commit or automatically cancel. So you introduce them, you just put the appropriate keyword before a block, and that is now part of the transaction. It behaves as if it's if there's a global mutex on the synchronized block. Atomic blocks execute atomically and not concurrently with synchronized blocks. Again, so you stick your keyword on and declare the block. It's very, very straightforward to use. But atomic blocks are lower level, so they can potentially execute concurrently with each other if they don't use the same variables. And they differ in their behavior with exceptions. So obviously no except, you're saying there won't be any exceptions, so it's undefined behavior. And then you can either commit or cancel when an exception escapes. But even on those cases, if you're trying to, if the exception is allowed to escape for a cancel, then it must be a special type of exception that's transaction safe, because otherwise the cancel transaction will roll back the creation of the exception that was going to be thrown. So you don't want that. Okay, so I reckon there's about 2 minutes for questions. Anybody got to get any? Yes. Okay, so the question is, obviously the operating systems provide us a whole bunch of things that we could potentially wait for. So we could wait for things coming from a socket, we could wait for things coming from a file and all sorts of stuff. And so is there any means of, in standard C++, of capturing that? And I think I have to say no. I think you look at the various TSs, so like if you're looking at waiting for the network, then you look at the networking TS and you use their facilities, which will wrap the OS. And likewise, if you're, but there isn't a general framework for capturing OS waitable things. Would you be able to use networking with the futures? Probably at the moment, no, but I imagine that sort of integration, when everything gets moved into the C++ standard, then that would be something that we were looking at, the integration between the different parts. But not at the moment. They're different TSs, so they don't talk to each other. Okay. Yes, there's a question over there at the microphone.
Yes. First, I would like to point out that make exceptional future is probably the coolest name in STL, so please keep it. And my question is regarding shared time mutex.
Okay.
I'm not sure I get it correctly, but so when you request a write lock, you still don't get it because there are some read locks on it, but you're requesting it, so you're waiting for the read locks to finish. Yeah. Does this mere fact prevent newer read locks to be created already, or can it be a starvation that you just keep waiting and waiting?
That depends on the implementation, and obviously, avoiding starvation is a key feature that implementers are going to want to do. There are techniques to avoid exactly what you said, so that if a waiter is waiting, then further readers cannot acquire the lock, and they have to wait too. So you can implement it like that, but sometimes there are reasons why you might not want to. You might want your readers to starve or your waiters to starve because of the way that your system is structured, and you know that eventually it will get to the point, and no, so.
And there is no way in the standard to specify which
there's no way to specify. You have to look at what your implementer does, and if you've got a choice of implementations you can use, choose the one that has the properties you want. Otherwise, yeah, you have to hope it's quality of implementation and not specified.
Okay, thanks.
So when an exception gets propagated from thread to thread when you're using futures, is it exactly the same exception with the same type, or is it some sort of a wrapping object?
Okay, it will definitely have the same type, I will say that, and on some platforms it will be really, really the same object that is rethrown. I think GCC does that on Linux. It counts the exceptions. So you catch an exception, you stick it in a future, you then call get, and it rethrows the same object. On other platforms, like say Visual Studio on Windows, then it will use internal stuff to copy the exception. So when the exception is rethrown, it is a copy of the same type. But it will always have the same type.
Does when any return the thread that triggered it, or does it just return a thread that's ready at the time that after it was triggered?
Okay, so yeah, so when any, it will, yes, the result will have a flag that says which of the futures it was that triggered it, and then it returns all of them to you. So you know which one was the one that triggered, but then more than that might be ready by the time you look at the result. Does that answer your question?
Yes.
I have a really quick question about the when any also. Is there any expectation of fairness in terms of, like, if there's multiple things waiting, is there some expectation that these things will be kind of generally fair?
Not over and above anything that your OS provides. So it's probably going to use the underlying OS waiting facilities. So no, on Windows, for example, you probably might end up using the equivalent of wait for multiple objects. So it doesn't provide you any more fairness than that would.
Okay, thanks.
Yes.
When you call get and an exception is rethrown, do you still have the original backtrace from the original throw point, or is it rethrown from get?
I would say that probably depends entirely on your implementation. With GCC, it's possible because it's the same object. It might still have the same backtrace available. I haven't checked, but if it's a fresh object because it's a copy, then it definitely won't have, unless you did something to capture it in your exception yourself manually.
Very simple question. How come nobody implemented or proposed a semaphore?
Because they didn't. It's just, yeah, and the C++11 library was based on Boost, which didn't have a semaphore, and nobody's bothered writing a proposal to have one since. So that's the fundamental reason there's no proposal for it. Okay, so it looks like we have no more questions. There we are.